Video anomaly detection, VAD for short, is a very important topic in computer vision, especially for safety-critical systems. There are two challenges, as abnormal events are infrequent in number and unbounded in category. Compared to normal events, which are more common, we can hardly collect a large number of abnormal data for training, and we cannot anticipate what types of abnormal events will appear. Basically, VAD is often taken as one-class learning problem, where only normal events for training, while both normal and abnormal events are presented for testing. Here we show several examples from 4 datasets. The typical abnormal events are car eroding in a pedestrian area or person rushing on the station platform. Currently, reconstruction-based and prediction-based methods often will reconstruct or predict the anomalous examples, though they are only trained on normal data. Recently, some works have explored self-supervised learning, avoid perplexity generation. However, they still suffer from 2 major problems. They model the pretext task as a binary classification problem and cannot learn highly discriminative features. They also depend on pre-trained networks, which cannot adapt to situations with large domain gaps. A question is naturally raised: what makes for a proper pretext task for VAD? We identified 2 key factors. The first is the moderate difficulty. To the end, we leverage jigsaw puzzles with full possible permutations. The second is motion and appearance modeling. We propose decoupled spatio-temporal jigsaw puzzles. A typical solution is treating solving puzzles as a multi-class classification, where each permutation corresponds to one class. However, its complexity scales factorially with the input length. To use all possible permutations in a more computation-friendly way, we cast multi-class permutation as a multi-label one and predict the absolute position in the arranged known sequence, which reduces the complexity from factorial to square. Our methods has several advantages. We simplify the self-supervised learning framework by solving only one single pretext task. We learn normal appearance and motion cues by decoupled spatial and temporal branches. We use full possible permutations to produce puzzles of various difficulty levels. We avoid the use of any constrained networks. We also deliver competitive results on 3 real-world benchmarks. Our whole pipeline is divided into 3 parts. The first is object-centric cube extraction. We first use an off-the-shelf object detector like Uno to localize all objects in the frames and stack the resized bounding boxes along the time dimension. The second is fine-grained decoupled puzzle construction. We decouple the puzzles into temporal and spatial sub-puzzles. For the temporal branch, we shuffle the frame sequence without disorganizing the spatial contents. For the spatial branch, we shuffle the spatial layout while keeping them in the chronological order. The last is multi-label supervision. We train the model to predict the absolute position of each frame or the location of each patch. We simply use cross-entropy to train our models. During testing, we select the minimal prediction score towards the unshuffled frames or images as the regularity score for the objects. Abnormal events are expected to have lower confidence scores as they are unseen in training. We also aggregate the regularity scores from both spatial and temporal branches. Clearly, we achieved the state-of-the-art performance on all 3 datasets. Especially, we outperform the reconstruction-based or prediction-based or hybrid methods by large margins. Here are the visualization results. Our predictions correlate strongly with the ground truth temporal segments of anomalous events. We also investigate 5 key factors that control the puzzle difficulty, such as the number of permutations or number of frames or patches. For more information, you may refer to our main paper.